Okay, so everyone's good with the idea of a reciprocal and how to calculate it? Yeah? So Zoe, 2/3, what's the reciprocal? Yeah? 3/2? 3/2? 3/2? No, 3/2 is right by me. Sam, what's the reciprocal of 4? Excellent, 1/4 or a quarter. Arat, what's the reciprocal of X? Yeah, brilliant. Siggy, what's the reciprocal of negative 2X? Close. Someone correct Siggy. Thanks, Elizabeth. Yep, -1 on 2X. And just be mindful, please, that you get that, and Elizabeth said it perfectly, that 1 on -2X is, I guess, the technical reciprocal, but a negative denominator is the same as a negative, putting the negative outside the fraction. Okay, just think about it in terms of a fraction being a division, and when you divide two numbers, if one of them is negative, the result is negative. So whether there's a negative on the top or the bottom, the whole fraction is negative. If there was a negative on the top and the bottom, the result would be positive, right? Okay, so just keep that in mind. Not that it's necessary to know that straight away. Okay, so this unit is it's a functions unit. It's a function that you haven't tackled in grade 10 maths extended, and they're called reciprocal functions. Shock, shock. Which is actually a subset of something else we're going to look at, which is rational functions. So understanding the reciprocal is kind of why I got you started there. But reciprocal functions, like I have tried to do in the past, I'm trying to get you to see the big idea first, just briefly, and then we'll get into the nuts and bolts, and then we'll come back and revisit the big idea, I suppose, as we go along. And reciprocal functions, as we know, functions in general, unless you're a mathematician who just loves just playing around with numbers and number ideas and stuff, in terms of how they apply to real life, we know that we study functions because functions are used to model context. Okay, so for example, growth of a population is modeled by what kind of function? Exponential. Thank you, Lily. Say hiring a bike would be a linear function, a linear model, usually, that kind of thing. It's directly proportional. You know, the number of hours that you hire a bike would be represented in a function, so it's directly proportional. There's a direct variation between the two variables. In the case of in the case of reciprocal functions and rational functions, we have this idea of inverse variation, and that's what I'm going to tackle now through through this big idea that we're going to tackle. And I'm just going to go through a couple of scenarios with you. One very simple one, the Lawler cleaning situation, and then a slightly more complex version. And I'm going to just lead you through it, and we're going to get an idea of reciprocal functions as a result. And I should say that thanks to Eddie Wu, really, because I was trying to figure out what's the best big idea I can use to try and unpack this. I'd say this is a medium idea, by the way. It's not a really huge idea, but it'll illustrate it quite well. And his approach it was actually pretty good, so I used his idea. And this won't be on the video, but I'm just going to flick through to this post here, inverse variation. This is your schedule of work. It has the textbooks practice work on here. It also has links to videos as well. So whatever we talk about here, I'll also put a link to the video I'm creating right now, so our actual class discussion. But yeah, all practice work and videos that might give you a bit of a better background than what, a refresh what we talk about in class will be available in your schedule of work. And your schedule of work is on Google Classroom. So I will be referring to that a fair bit. So do make sure that you utilize that when you can. That's just been posted just now. Getting back to the Lawler cleaning situation. So last year, for better or for worse, my family of three kids, my wife, Sharon, myself, moved in. Sharon's an only child. We moved in or they moved. Well, we combined our resources with Sharon's parents, and we combined our resources, and we now live in a nice big house down in Acton Park. So all 7 of us, all 7, including my parents-in-law. That's fine. We're not here to discuss my personal demons. This is more about what that means for our house. Having a house of seven people in it, you know, we get cleaners in once a week. I think that's a reasonable thing to do. And the cleaners, we pay the cleaners for 4 hours of cleaning per week. Okay, 4 hours of cleaning. 2 cleaners come to do the job. How long are they there for? 2 hours. Now, the old-fashioned phrase for this, which we're not going to use other than right now, is, but you might see it here and there, is man hours, which is pretty sexist. I think work hours is probably the best way to talk about it these days. I think it's better than person hours, isn't it? So work hours. So I don't pay for 4 hours of a cleaner. I pay for 4 work hours. So if 2 cleaners come, that means they'll stay there for 2 hours. And if 1 cleaner comes, they would stay for 4 hours. Does that kind of make sense? Yeah. And if for some reason they needed to get the job done really quickly, I could get 6 cleaners to come in or 8 cleaners to come in, and it would take a proportional less amount of time to do it, right? Let's have a look at a more complicated example, though, I think. That will make it a little bit more to sink your teeth into. So this is sort of a classic example, but it's this idea of apportioning work to workers is a pretty common one. So it's worth having a look, and it does illustrate this idea of what is called inverse variation, which is what reciprocal functions model, inverse variation. So 4 painters take 12 days to paint a house. How many days will it take 6 painters to do the same job? You have to calculate it. What's your estimate? What do you think? What's the estimate here? Anyone want to take a chance? Lily reckons 8. Who agrees with Lily? No one. You're on your own, Lily. Anyone have another guess? 6? Oh, okay. Just an estimate. So I'm not going to waste any more time than that. It's just an estimate. So let's see if Lily's right. Lily, you're the only person who's going to put a number to it. Let's see if you're right or not. Okay, so let's sort of structure this a little bit more specifically, and we'll have a look at what do we know? We know that 4 painters will take 12 days. So let's solve a simple related problem. How long would it take 8 painters? I might call on people here. I think this is not too troublesome to people. So I might just call on people, and it's okay if you say, oh, look, I've got no idea. But I'll start with you, Will. How many days would it take 8 painters? 6 days, yeah. Does that make sense to everyone? 6 days for 8 painters? Okay. What about, let's just say, you've hired this company to paint your house, and they say, oh yeah, we'll get it done in 12 days with 4 painters. Then they call back and say, actually, all of our painters have come down with some sort of illness. Well, we'll only be able to give you 1 painter. So how long would it take 1 painter to do the same job, right? Yeah. Does that make sense? Yeah, okay, cool. So 48 days. All right. Let's try 2. 2 painters. How long would it take 2 painters to do that? Sam? 24 days. Sounds good to me. And there's a couple of ways we could have got to that, isn't there? We could have gone, well, I've got half the painters that I started with, So I've doubled the number of days it's going to take. Or you could use, and you might have remembered this from year 8 even, where you did ratios. You've got the unitary method, which says if I've got one painter, then I can just scale up from 1 to any number I want to. So one painter for 48 days, double that, there's 2 painters for 24 days. Yeah? Okay, so what we were asked was how long would it take 6 painters, and Lily said 8. Was she right? Paraf, was she right? Because that was so confident. So confident. So we've got one painter here. If I times this by 6, I get my 6 painters. And if I divide the number of days by 6, 48 divided by 6 is 8 days. So Lily, you're right. Well done. Okay, so we've got a sense here. What's the relationship? Who can see the pattern or the relationship between the number of painters and the number of days? That's true, Lily. Arif? That's the other truth as well. So there's 2 things here. First of all, the relationship between both of them is that if I multiply, I get 48 every single time. Can we see that? So there's a relationship here that says that if I call the number of painters P and the number of days D, then we would say that P multiplied by D is equal to 48. Like so. Now, Lily said that if you halve one, you increase the other, or vice versa. But you could also say the same thing for a fraction, any fraction, couldn't you? If you, or multiplication. If I'm going up, if I'm upping one, I'm downing the other, right? So I could go from, if I'm increasing the number of painters, say here and here, I'm decreasing, I better choose a different colour so it stands out. I'm decreasing the number of days. Will? Yeah, great, great. That's, I really like the language of reciprocal there because we're going to come back to it. But to simplify what you said even further, if I multiply the left-hand side, I divide the right-hand side and vice versa. Yeah. So there's this inverse relationship between them. Okay. And that's why we call this kind of problem an inverse variation problem. As one side increases, the other side decreases at the same constant rate. Okay, same constant rate. Okay, what I can do is I can rearrange this formula here and say that, which one do you reckon is the independent variable? I reckon P must be, mustn't it? The number of painters is what you throw at a job, and then the days vary as a result. So let's put D on the left-hand side. D is equal to 48 over P, as long as P what? Well, just not equal to 0 is all I was thinking. Yeah, true that. But at the very least, our basic understanding is I can't divide by 0. Yeah, I can't divide by 0. So the number of days is equal to 48 divided by P, and there's a reciprocal kind of relationship there, as Will pointed out. Does that kind of make sense? So this is inverse variation. Now, really briefly, I'm going to show you a video, if I can. It might be too laggy, we'll see. So I'm going to pause this video. So just for the recording's sake, I'll just say we can go to, if you go to the work schedule, the video is, it's the Khan Academy video on the work schedule. Okay, so Khan Academy video shows that it's basically like a function. So what we talked about just before I went and showed you the Khan Academy video is this idea that we chose D, the number of days, even though time is often is actually usually the x-axis, isn't it? But in this case, it makes more sense for it to be the y-axis. We've got D as being the dependent, and we said that D could be calculated by dividing 48 by the number of painters you've got. D equals 48 over P. So in terms of sketching it, as someone said, could have been Zoe, said that we're not going to have negative painters. So let's just have a look at the positive axes here. So this is what we call first quadrant. We've got days up here and painters here, and our graph would be like this. Does that kind of make sense? The more painters I've got, I'm just going to be reducing the number of days that will be required to undertake the job. Or as I increase the number of days, I'm going to be pulling back the number of painters. I guess there could be a scenario where you say, I just want you to, you've got the next 3 months to do it. You put as many painters as you need in order to get the job done in 3 months, please. And they say, oh, well, okay, we'll get someone to come in for a couple of hours a day. So 1/3 of a painter, effectively. You know what I mean? Not a full day. Okay, and then we'll make sure it's done in 3 months, something like that. So does that graph kind of make sense? Okay, so if we had 48 painters, for example, that'd be somewhere here, right? Let's just put it here. This would be 48 painters, and it would take 48 painters how many days? 1 day, yeah. So that would be like 1 there and 48. Now, logistics aside, i.e., there's got to be a limit, doesn't there, where you've got so many painters in the house that they actually can't paint. But let's just ignore that. Let's pretend that that's not an actual limit. So if I had 96 painters in the house, how long would it take the 96 painters? Lily says 24. You need to go to a different company if that's the case. It would take half a day, wouldn't it? If it takes 48 painters 1 day, it would take 96 painters half a day, wouldn't it? What about 100 painters? Don't give me a specific number, but it'd be less than half a day, right? 200 painters, a bit of a day, a couple of hours. What happens if, again, realism aside, what happens if we had all of Hobart going in to paint your house? Then it would take maybe just a minute or two, right? I mean, realism aside, a minute or two. But the point is, yeah, without COVID social distancing rules either. So, but the point is that if I had all of Tasmania coming into paint or all of Australia coming into paint, I'm going to get a smaller and smaller and smaller fraction of time, right? But it's never going to be 0 or negative in this instance, but it's never going to be 0. In other words, as I increase the number of painters, as I increase this, the number of days is going to approach 0 but never hit 0. Does that sound like this concept we've covered before? When a function approaches a value but never actually hits it? Siggy?
Oh, yeah. I've sort of a different point. Surely if hundreds of people go through your house and they're only there for 10 seconds, they unpack their stuff, pack it back up, go out, and they just leave their money booster. So surely they're just making negative work.
Making negative work. We're not painting the floor, Siggy. Duh. Okay, so moving back. Does this concept sound familiar at all, where we have this idea where it's approaching a value, in this case 0, but not actually passing it? Anyone remember the special word we use that people always often mispronounce? Arit? Yep, asymptote, and you pronounce it properly. Yep, asymptote. So we have a horizontal asymptote, right? The number of days will never reach 0, and so I can put a dashed line along here, and I'll say D equals 0. So remember, horizontal asymptote, the equation is always going to be whatever the y variable is equals 0, equals that value, okay? So D equals 0. And we could probably argue the same way, right? We could say one painter came in every half day. Or, that means you'd effectively have half a painter effectively per day. Does that kind of make sense? It's kind of a similar relationship. A painter came in every other day, every second day. That's an average of half a painter per day. Or a single painter came in once a week. That'd be on average a seventh of a painter every day, on average. Yeah? Or they came in once a year and painted it. Then that would be on average 1/360. So do you get what I'm saying again? That, you can also argue the same way as well, that as long as the painter's still coming in, even if it's like once a century, realism aside, obviously the painter would die before then. But the point is, if whatever you're doing, the job will probably eventually get done, but it's going to take thousands of days or centuries or whatever else to get done. Not realistic. But the point is that in this scenario, we can see that P, the number of painters, will not get to zero, but as it approaches zero, the number of days approaches infinity. Yeah? So like a logarithm graph, we have a vertical asymptote. And this is another feature of a reciprocal or rational function. It has both a horizontal asymptote and a vertical asymptote. Vertical asymptotes are where the x-axis the x variable cannot reach. In this case, the x variable is p. So this is at p equals 0. So we have a horizontal asymptote and a vertical asymptote at those 2 points. Does that kind of make sense to everybody? Okay, so theoretically, if I keep on reducing the number of painters, then the number of days is just going to get bigger and bigger and bigger and bigger and bigger. And as long as we've got a painter committed to a particular job, even if it's like thousands of days, it still makes sense in a broad contextual way. Okay. That is it. I'll pause the video now. What we're going to go do now is we're going to go to the textbook, page 190, just for the video's sake. I'll keep this on the video. We're going to have a look at the graph on page 190, and it's going to point out features. I won't be able to put that into the video because you won't be able to see it. But that's where the graph of the reciprocal function is, including thinking about it on the other 2 quadrants as well, other 3 quadrants as well. So let's do that, and then we'll get you into some work to finish off the lesson. Stop.